In this electrical analysis, we are examining a 400 amp service and its compliance with the National Electrical Code, specifically sections 310.15 and 230.90. The configuration involves two 200 amp main circuit breaker panel boards. From the service point to the meter socket, parallel 2/0 American wire gauge conductors are used for the ungrounded conductors. On the load side of the meter socket, single 3/0 American wire gauge conductors are installed to each 200 amp panel board. The total calculated load is 250 amps. The question is whether this arrangement meets all the requirements of the National Electrical Code. Let's delve into the specifics. Firstly, consider the parallel 2/0 American wire gauge conductors from the service point to the meter socket. These conductors will not be loaded to greater than 250 amps and have a derated ampacity of 280 amps. At first glance, this seems to comply with exception number 3 to 230.90a, which allows for reduced ampacity in certain service conductor configurations. Secondly, the individual service entrance conductors to each 200 amp panel board must comply with the 310.16 ampacity rating of 200 amps or the appropriate conductor size based on the tables. Now let's examine the reasons why this arrangement, as described, does not meet all the requirements of the National Electrical Code. One of the key factors is the installation method of the paralleled conductors. According to 310.15b exception number 3, conductors larger than 1/0 American wire gauge in parallel must be installed in conduit or a raceway. The parallel 2/0 American wire gauge conductors in the described scenario do not meet this requirement if they are not installed in conduit or a raceway. This is a critical point of non-compliance. Additionally, let's consider the service entrance conductors to each 200 amp panel board. According to 310.16, the service entrance conductors must have an ampacity of at least 200 amps. The 3/0 American wire gauge conductors have an ampacity of 225 amps, which does technically meet this requirement. However, the primary issue lies with the installation of the paralleled conductors. It's important to remember that the National Electrical Code sets minimum standards for electrical safety. Proper installation methods are just as crucial as selecting the correct conductor size. The requirement for installing parallel conductors larger than 1/0 American wire gauge in conduit or a raceway is in place to ensure the safe dissipation of heat and to provide physical protection for the conductors. Now let's discuss 310.15, which covers ampacity calculations and adjustments for conductors. 310.15 outlines the general requirements for ampacity, stating that conductors shall be protected against overcurrent in accordance with their ampacities as specified in the allowable ampacity tables 310.16 through 310.21. This means that the conductors must be sized and protected in such a way that they can safely carry the intended load without overheating or posing a fire hazard. 310.15b addresses correction factors and adjustment factors. These factors come into play when the ambient temperature is higher than 30 degrees Celsius or 86 degrees Fahrenheit, or when there are more than 3 current-carrying conductors in a raceway or cable. In these situations, the ampacity of the conductors must be reduced to account for the increased heat. Exception number 3 to 310.15b, as previously mentioned, specifically addresses parallel conductors. It states that conductors installed in parallel shall be subject to the ampacity adjustment factors as required in 310.15b3, which deals with the number of current-carrying conductors in a raceway or cable. However, it also provides an exception allowing for the ampacity adjustment factors not to apply to conductors in parallel if certain conditions are met, namely that the conductors are installed in separate raceways or cables and the ampacity of each conductor is derated to 80% of the allowable ampacity in 310.16. In the scenario we are analyzing, the 2/0 American wire gauge conductors in parallel would need to be installed in conduit or a raceway to comply with this requirement. Now let's move on to 230.90, which deals with overcurrent protection for service conductors. 230.90 states that service conductors shall have overcurrent protection in each ungrounded conductor at the point where they receive their supply. The overcurrent protection device, typically a circuit breaker or fuse, must be sized to protect the conductors from overcurrent conditions such as short circuits or overloads. Exception number 3 to 230.90 allows for the overcurrent protection device to be sized higher than the ampacity of the service conductors in certain situations. Specifically, it states that where the service supplies power to multiple buildings under single management, the overcurrent protection device can be sized up to the sum of the feeder overcurrent protection devices protecting the feeders supplying each building. However, the conductors must still be sized to carry the calculated load. In the case of our 400 amp service, the parallel 2/0 American wire gauge conductors have a rated ampacity of 280 amps, which is greater than the total calculated load of 250 amps. Therefore, this aspect of the installation would comply with exception number 3 to 230.90a. It's important to note that the National Electrical Code is a comprehensive document that covers a wide range of electrical installations. It's essential to consult the specific sections and exceptions that apply to each situation to ensure compliance. In addition to the requirements we've discussed, there are other factors that could affect the compliance of this installation. These include the type of insulation used on the conductors, the ambient temperature, and the presence of other conductors in the same raceway or cable. To ensure compliance, it's always recommended to consult with a qualified electrician or electrical engineer. They can assess the specific conditions of the installation and provide guidance on the appropriate conductor sizing, overcurrent protection, and installation methods. Furthermore, it's crucial to stay up to date with the latest edition of the National Electrical Code, as the requirements can change from one edition to the next. Continuing education and professional development are essential for anyone working in the electrical industry. Let's recap the key points of our analysis. The 400 amp service configuration, as described, does not meet all the requirements of the National Electrical Code due to the installation of the parallel 2/0 American wire gauge conductors. According to 310.15b exception number 3, conductors larger than 1/0 American wire gauge in parallel must be installed in conduit or a raceway. The 3/0 American wire gauge conductors to each 200 amp panel board do meet the ampacity requirements of 310.16, as they have an ampacity of 225 amps, which is greater than the required 200 amps. In conclusion, it's crucial to pay attention to both conductor sizing and installation methods when designing and installing electrical services. Compliance with the National Electrical Code is essential for ensuring the safety and reliability of electrical systems. Now let us think about different insulation types of the conductors. The insulation type on a conductor impacts its ampacity rating. Common insulation types include THHN, THWN, and XHHW. Each has different temperature ratings, influencing how much current the conductor can safely carry. For example, THHN and THWN are often rated for 90 degrees Celsius in dry locations, allowing for a higher ampacity compared to conductors with lower temperature ratings. However, the termination temperature rating of the equipment, such as the panel board, must also be considered. If the equipment is only rated for 75 degrees Celsius, the conductor ampacity must be based on the 75 degrees Celsius column in the ampacity tables, even if the conductor insulation is rated for 90 degrees Celsius. The ambient temperature also plays a significant role. The ampacity tables in the National Electrical Code are based on an ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit. If the ambient temperature is higher, the conductor ampacity must be derated using correction factors provided in 310.15b2. These correction factors reduce the allowable ampacity to account for the increased heat. The number of current-carrying conductors in a raceway or cable also affects the ampacity. When multiple current-carrying conductors are grouped together, the heat generated by each conductor can raise the overall temperature inside the raceway or cable. This necessitates a reduction in the ampacity of each conductor to prevent overheating. 310.15b3 provides adjustment factors for different numbers of current carrying conductors. For example, if there are 4 to 6 current carrying conductors in a raceway, the ampacity must be derated to 80% of its original value. It is also important to correctly identify the current carrying conductors. Neutral conductors are generally not considered current carrying conductors unless they carry a significant amount of harmonic current. Grounding conductors are also not considered current carrying conductors. Now let us look at some hypothetical scenarios. Consider a situation where the 2/0 American wire gauge parallel conductors are installed in separate conduits and the ampacity is derated to 80%. In this case, the ampacity of each 2/0 American wire gauge conductor would be reduced to approximately 152 amps. Since there are 2 conductors in parallel, the total ampacity would be 304 amps, which is still greater than the calculated load of 250 amps. In this scenario, the installation would meet the requirements of the National Electrical Code, assuming all other requirements are met. However, it is important to consider the voltage drop. Voltage drop is the reduction in voltage that occurs along a conductor due to its impedance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The National Electrical Code recommends limiting voltage drop to 3% for feeders and 5% for branch circuits. To calculate voltage drop, you need to know the conductor length, the current, and the conductor impedance. There are various online calculators and software programs that can assist with voltage drop calculations. If the voltage drop is excessive, you may need to increase the conductor size to reduce the impedance. Another important consideration is short circuit current rating. The conductors and equipment must be able to withstand the high currents that can flow during a short circuit. The short circuit current rating of the equipment must be greater than the available short circuit current at the point of installation. Short circuit current calculations can be complex and require specialized knowledge. It is recommended to consult with a qualified electrical engineer to perform these calculations. Let us also address grounding and bonding. Grounding and bonding are essential for electrical safety. Grounding provides a path for fault current to flow back to the source, allowing the overcurrent protection device to trip and clear the fault. Bonding ensures that all metallic parts of the electrical system are at the same potential, reducing the risk of electric shock. The National Electrical Code provides detailed requirements for grounding and bonding in Article 250. It is important to follow these requirements carefully to ensure a safe electrical system. The size of the grounding conductor must be based on the size of the service entrance conductors. The bonding conductors must be sized to adequately bond all metallic parts of the electrical system. It is also important to properly bond any metal water pipes or gas pipes that may be present. Remember to consider future expansion when designing an electrical service. It is often wise to install a larger service than is currently needed to accommodate future loads. This can save money and time in the long run, as it avoids the need to upgrade the service later. When planning for a future expansion, consider the potential for adding new equipment or increasing the load on existing equipment. Also, remember to account for any changes in the building's occupancy or use. By carefully considering all of these factors, you can design an electrical service that is safe, reliable, and compliant with the National Electrical Code. Finally, let us summarize the key takeaways. The 400 amp service configuration, as described, does not meet all the requirements of the National Electrical Code due to the installation of the parallel 2/0 American wire gauge conductors. Conductors larger than 1/0 American wire gauge in parallel must be installed in conduit or raceway, according to 310.15b exception number 3. The 3/0 American wire gauge conductors to each 200 amp panel board do meet the ampacity requirements of 310.16. Always consult with a qualified electrician or electrical engineer to ensure compliance with the National Electrical Code. Consider all relevant factors, such as conductor insulation type, ambient temperature, number of current carrying conductors, voltage drop, short circuit current rating, grounding, bonding, and future expansion. By following these guidelines, you can ensure a safe and reliable electrical system.